Hello and welcome back to Calculus 1. We're looking at section 3.9, derivatives of exponential and logarithmic functions. We already know that the derivative of e to the x is e to the x, but then we can do more and we can do other cool stuff. So let's see, there are other bases. So what we know so far is that the derivative of e to the x is e to the x, and you also memorized, which you don't have to know anymore because you can use chain rule, is that the derivative of e to the ax is a e to the ax. So that's what you know so far. But we can actually do better. We can say, what is the derivative of e to any function f of x? And now you see that you have to use the chain rule because f of x is plugged into e to the x, so the derivative must be e to the f of x times f prime of x as a chain. And that is a big formula right there. It's chain rule. Yeah. Exactly. But then you say, well, why always e? Can I find the derivative of 2 raised to the sine x? And I say, yes, you can. Actually, the box on this one was supposed to be red. The next one is b raised to the f of x, where b is any value. And this is the one which would have 2 to the sine x, or 1/2 raised to the x squared plus 3x minus 5. So this is actually the boss equation. This one is the most general exponential case that you can get. And every other case above this one is kind of too specific for exponentials. So the derivative of this would be b f of x times ln of b times f prime of x. And that is the boss equation. What happened? ln. Natural log. B is any base.
Like 2.
Yes. Or?
3.
Yes. Or?
4.
Very good. So, anything other than e, right? Because when you have e, it simplifies to these formulas up there. But if you have anything else other than e, this is the formula, right? So, that's that. And now for logs, the inverse of exponential function. First off, logs. What's all of the fuss about that, and why is it so scary? It shouldn't be. Let's just have some algebra / arithmetic first. So if I am to add 2 plus 3, I will get 5. And then if I am to subtract 2, I can get 3. And if I am to subtract 3, I can get 2. As you can see, you guys have opposite operations addition and subtraction can extract and give you back 2 and 3, which were the two input numbers for addition. What's 2 times 3? 6 divided by 2 is, and 6 divided by 3 is. So now you see that you can again get 3 and 2 back from this calculation. Now, multiplication was the higher order operation, right, than addition. But multiplication is some kind of fast addition, right? But now I can say 2 cubed is equal to 8. So this is repeated multiplication. It's like an uber fast addition. Now you can take a cube root of 8 and get 2. How do you retrieve 3? You gotta use a log. Log base 2 of 8 is 3. What is log? It's just a mathematical operation. Except looks weird because we are using letters. We are not using a symbol. Log is the way to combine two numbers and get a third number, just like any other operations that you see there. You see addition, subtraction, multiplication, division, squaring, square rooting, and everything else, right? Those are all mathematical operations that take two numbers and give us a third number in return as the answer. Well, log does the same thing. You combine this number 8 and number 2 in a specific way, and you get 3 back. So we shouldn't be discriminating against log as something special or something crazy. It's not. It's a way to change two numbers into a third number just like any other operation. Logarithm is not a function. Logarithm is the operation that you use in between 2 and 8. Now, if that was, some different symbol, maybe it would be more easy to understand. So what we are doing here is we are literally taking number 2 and a symbol and then number 8, and we are getting 3. All right? If that was a symbol for log, it would be much better accepted, I guess, right, in the community. So we are combining two numbers. We are combining two numbers with log to get a third number. Now, observe the first column. I can make this into a function by either writing 2 or 3 as x. So if I write y equals x plus 3, this becomes, all of a sudden, a function. Up there was calculation, and you understand that, because 2 plus 3 is 5. No need to invoke functions and things. On the other side, I can write y equals, let's say, 2x. Right? I replace 3 with x. And there you go, I have a function again. On this one, I go y equals 2 to the x. That's your exponential. So log is not a function, but if you involve x, it becomes a function just like all others. Because log is not special. Log is not special. It's just mathematical operation. All the rules that hold for mathematical operations, other mathematical operations, they hold for log. None of these here are functions. It's all calculations. And log is in that basket. And as soon as you involve x, then they become functions. So now, I will write the logarithmic function y equals ln of x. That has the graph and domain and the range and all of the cool feature like any other function. So logarithm is not a function, it's operation to change two numbers into a third number. So you're combining two numbers into a third number in whatever rules apply for log calculations. And then you get to make a function out of it once you introduce x and you say ln x or log base 7 of x or something like that. Now, what you are supposed to know for today's class is the 3 rules of logs that help you expand and contract logs if you have multiple logs of the same base. Rule number 1 says that ln of f times g is equal to ln of f plus ln of g. So the product of arguments, right, goes into addition or sum of logs. Number 2, ln of f divided by g by common sense is what? Negative. Very good. Making sure g is not 0. And the third rule is going to kick the exponent outside. So if you have some power p, p will jump in front of the log. Now you need to know these 3 rules to be able to solve not implicit differentiation, logarithmic differentiation. So they will play a crucial role. What do we have? Another 4 minutes? And then another 30 minutes after that. So now we are memorizing and building up the derivatives of logs. We start with the simplest one, which is still used a lot, which is what is the derivative of ln x? So you have a natural base e there, so that's why we put ln. If you are using any other base other than e, you actually have to go with the log and use the number for that you had as a base. Does anyone know what's the derivative of ln x? 1 over x. Very good. Oh, we can do better. We can ask what is the derivative of ln of some random function f of x. What now? Yes? Times derivative, yes. So 1 over f of x times the derivative of f of x. So it's easier to just say derivative divided by the argument. Now that's one of the major formulas. So it's going to get the red box. And it's a formula that you guys are going to use all the time. Now as a student, I absolutely love ln because the way to take the derivative, I mean, you have to memorize this. And the way you take the derivative, look, that's the argument, right? Whatever is after ln. Look, Control C, Control V, right? And then you take the derivative on top. Control C and Control V in when you have the actual computers, that means copy and paste. Not sure if your garbage apple top has that yet in programming. So there we go. That's the major formula that will be used a lot. You can quickly find that the derivative of ln cosine is negative tangent, like this. Right? Good. What's the derivative of ln of cosine x? I have them chiseled, I don't remember them. Yeah. Do some chiseling as well. You missed the negative. So sine divided by cosine. There it is. I bought it. I was actually so much out of stock that I was waiting for 3 months to actually get it. I bought it and I waited 3 months.
Seriously? Apple's a great brand.
I can't wait to get this one.
There's implicit cost and explicit cost.
So the derivative, oops, let's do this example real quick. So the derivative of ln of cosine x is, you copy the argument and you put the derivative in the numerator, which quickly works out to be just negative tangent x. It is very simple to take these derivatives. And now you would say, well, wait, ln means base e. What do I do if I have base 2, base 7, or something else other than e? Which is where the boss equation shows up, the one that has b again. So just if you're still having trouble with ln and stuff, ln x means log base e of x. It's just a lazy notation. It's 2 characters shorter to write because e has the most application. The base e has the most application, followed by base 10. If you took chemistry, you ran into pH calculations which use log base 10. If you took some of the physics, you ran into calculations for sound intensity and so on, the decibel scale, which again involved log base 10. Maybe you learned something about earthquakes and so on. So log base 10 is the second most important base, most frequent base. So that's why you have those 2 special notations. If you just have logx, that means log base 10 of x. And if you have ln, that's the natural logarithm because the base is e. But technically what you have is just y equals log base b of x, where b can be any value, not just e or 10. Could be 2, could be 1/3, could be pi. So it could be anything. And I want to know what is the derivative of the most general case we can have, and that is log base b of f of x. So this one has it all. And again, it's just Control C, Control V, and then the derivative on top times the ln of b. And that is the big equation.